the time that takes for you to end up with 1/2 of what you originally had either way. Okay. Now you guys look. So we're going to kind of do a little derivation. Once again, you guys, radioactive decay. It's a first order process. So because the concentration of A at time at the half-life, isn't it defined as 1/2 of what we originally had? So the concentration at time t, at the half-life, is going to be half of what we originally had. Okay. So now look what we can do. This is a first order. You guys, this is a little math here. When you have a log or a natural log of something minus that, you can rewrite it like this. When it's minus that, some of you guys who remember your math, you can just say the natural log of concentration of A at time t over the concentration of the initial concentration. So when you subtract it, you can just take the quotient of those two for the natural log, and that's equal to negative kT. So now look, and then the rest we'll do here. So you guys remember, so for on the half-life, the concentration at the half-life, the concentration will be half of what we originally had, right? So then look what we can do. So then, instead of putting the concentration of A at time t, can I just do 0.5 of the original concentration? It's half the original concentration. Divided by the original concentration, what's going to happen here, guys? I think you guys see. And that's just going to cancel out. So then I can just get the natural log of 0.5. You could plug that into your calculator. You just put 0.5 and you push the natural log button. You're going to get negative 0.693 is equal to negative kT. Notice, and for t, because we had already said this, we're doing this for the half-life, right? The time it took for us to have half. So I'll just call it t1/2. So it's equal to negative kT. So then I'll divide this by negative k. You guys see, divide both sides by negative k. Hopefully you guys see the derivation. And we end up with this equation right here. This is the equation you guys can use when determining the decay rate of a radioactive substance. And I'll put it right here. And you guys remember why? Because it's a first order process. And then what we did is we just derived it. And you guys, notice I asked a question. So what does the half-life depend on and what does it not depend on? You guys notice, look, what does the half-life of a radioactive substance simply depend on? Just K, just the, you guys remember what K is? That is the rate law constant. And look at this. You guys remember our rate law constant? Right, look. Remember when we had, this was the one we spent a little bit more time on. When you guys agree, the rate is proportional to the rate law constant. So if you increase the K, aren't you going to keep, like if we double K, you're going to double the rate. So those are proportional. Well, look at this, when you guys agree. So the higher, so we know the higher the K value, so if you have a high rate law constant, you're going to have a faster rate. Well, that should be consistent with what we see here. If we have a high K value, right, that means the reaction is happening quickly. When you guys agree, this is in the denominator. The larger the number is in the denominator, when you agree, the smaller is the overall number. So what does a large K correspond to? A large K corresponds to a fast reaction rate, which corresponds to a short half-life. Does that make sense? The half-life, the amount of time it takes for half of it to react is going to be much shorter. The faster it reacts, you're going to reach the halfway point much faster. And when you guys agree, a small K value corresponds to a slow rate. So the smaller this number is, when you guys agree, since it's in the denominator, the larger this value is. So the smaller the K, the slower the reaction rate, the larger the half-life, or the longer the half-life, the longer it takes for a substance to decay to half of what you originally had. So, what are we doing here? Yeah, okay, so we said that for a first order process and the half-life just, oh, and you guys notice, what does it not depend on, which seems kind of weird, but we'd already talked about it. Notice there's no concentration value here. It's not dependent on the concentration. Remember, the half-life of a radioactive substance is always a certain length of time, regardless of how much you have originally, okay? So it is not dependent upon the concentration. So, guys, we're gonna finish with this last problem. I know this is kind of long, but it's one of our longer ones. So what's the half-life of carbon-14? Guys, carbon-14 is a radioactive isotope of carbon. Most of carbon that we're made up of is carbon-12. Some is carbon-14, and carbon-14 radioactively decays. Here is the rate constant. You guys will notice, look, it looks like it's a very small number. So what would that probably tell you? Probably a slow reaction rate. So what does that tell you about the half-life? It's probably going to have a rather long half-life. So let's see. you guys, this is really easy. So I know I'm talking about a radioactive substance. I know I'm talking about a first order. And if I'm looking for half-life, couldn't I just use this? So it's really simple, guys. What you're going to do is, I don't even think I have to show you on the overhead. To get the half-life, I just go 0.693 divided by the K value, 0.000124, and that is 5,589 years. So what that tells you is if I had a certain amount of carbon-14, let's say I have 1 kilogram of carbon-14, after 5,589 years, I'm going to have half a kilogram. After another 5,589 years, I'm going to have a quarter of a kilogram. And so you're going to get half because that is consistent. Remember, that half-life is not dependent upon how much I have the concentration. It's only dependent upon the rate constant. Okay, last thing. When looking at a rate law, unless it is zero order, the rate of a reaction is affected by the concentration of the reactants. Think about a rate law. You see this is a second order. Notice it's to the second power. See the rate is dependent upon the concentration. Unless if it's zero order, okay, if it's zero order, this is a zero, and you don't even have a concentration of it. Like for example, well, we'll just leave it at that. But what else affects the reaction rate besides concentration? Last thing, guys, we talked about this before. What else affects the rate of a reaction that it doesn't look like you have it here in the rate law? When you guys agree, isn't it temperature? And the temperature affects the rate law constant. The rate law constant changes. This is the rate law constant. You guys notice, look, as the temperature increases, because you guys know the higher the reaction, the higher the temperature, the faster the reaction rate. That has an effect on the K value. So if you have a higher temperature, so basically, right, if you're going to state the rate of a reaction, when you guys agree, you probably have to indicate at what temperature, because the K value is temperature dependent. The higher the temperature, the higher the K value, the higher the K value, the faster the reaction rate. All right, guys, I think I took enough of your time. We'll see you guys next time.